All right, let's get started. How's everyone doing? How's everyone doing tonight? Great. All right. Welcome to week 3. Today I will be talking about some data structures. Not a surprise. Let's see. First, a word of caution. This is much simpler than what Ellen covered last week for Web trees. It'll be much easier to absorb, so it might be disappointing for a bunch of you. And for those of you who already know the structure I'm talking about, well, you might be bored as well. So just apologies in advance for that. But for those of you who don't know me, my name is Irham. I'm a year 3 CS student. I've been teaching together with Eldon for a bunch of semesters, and right now he is one of my materials. So yeah, let's get started. First off, a little bit of bookkeeping. At the end of the semester, as you know, you'll be doing a presentation where you'll be choosing some data structure of your choice and then presenting on it. So for the time being, try to take some time to maybe find your two-man team and then select the topic that you'd like to present. We should already have the list of topics on Piazza, or if not, I'll post it up. Or if you want something that's outside the list, sure, bring that up. We can put that in for you. Tentatively, we'll want a progress report by week 7. Week 7 should be right up. Week 7 is right after the recess week, so hopefully over there. All right. Are there any questions with regards to this one? If not, one additional word of caution. Unfortunately, I did not have enough time to make the slides as nice as I want to. So there will be times where I have to stop the presentation and then jump to the whiteboard and vice versa. So just a word of caution for that. And this is one of them. Right. Let's get started. For these coming weeks, mostly this week and next week, we'll be focusing mostly on range-based operations. That is, given let's say an array of elements, maybe you want to perform some operation on some range. Maybe you increase this by 2. Maybe you want to set all of them to find the minimum of this range. Maybe you want to set them to the minimum of this value or the original value. Those kind of things. The ones I'll be talking about today are the simpler ones, the ones that are nice and simple for you to get started. But first, let's talk about the motivating problem. So let's see. Message compression was a thing in the past. It's still a thing now. People have always been trying to find nicer ways to compress messages as much as they can. For those of you who have taken 3230, you might recognize the name Huffman coding to be an optimal way to compress individual characters. But of course, you know that there may be better ways to do that. That is, let's say you have the idea of contextual-based clues. The idea that instead of looking at each character individually, you can look at the entire message to find out what character comes next. For example, if I say that I have a message inside my mind and I would like you to guess the characters of it. For the first one, maybe you try to guess some random characters, maybe you try S, maybe you try R, and eventually after a bunch of tries you'll get the first character. But as it goes on, eventually there'll come to a point of time where you have enough contextual clues such that you'll know exactly what the next character is, or at the very least you'll have a higher probability of finding that. So in this case, the answer is A, of course. So that's essentially the direction that people try to go to when they try to compress messages. Just a show of hands, how many of you are familiar with the concept of arithmetic coding? I see half a hand. Yeah, that makes sense. Yeah, it's not exactly something that's very common, but that's the idea that sure. Basically, I'll give you a small example. Let's say your message can consist of these possible values. Let's say A, B, and C, and maybe some special character that says, is the end of the message. Okay. Let's say the same thing. Initially, you don't know what's going to come out. So maybe you want to assign, let's say 0.1 probability of an end of message, and maybe 0.3 of all the others. Okay. So from there you guess the first character, and let's say you find out that the first character is B. All right. let's say as you're trying to guess this message, we'll follow this protocol. You'll give more priority to the characters that you've seen more frequently. So in this case, after seeing B, you'd want to maybe adjust your frequencies to have a higher probability when trying to guess B. We can possibly do that by, let's say, maintaining the frequency of everything. Let's just say initially we start out at 1. So from there, your 0.9 is evenly distributed among them. After that, after you find the first B, you maybe update this to 2. And now you want to do the same. Now you want to do the same thing. Take that 0.9 and then distribute them based off of this idea. So let's say 0.5, this shall be 0.45, and this one 0.225, and so on and so forth. Then from there, as the message goes on, you can just adjust this accordingly. The idea behind arithmetic coding is that you can take the interval from 0 to 1, the real interval that is. Then from there, initially, we break that up into our individual probabilities as we. You saw nothing. Break that up into our individual probabilities as given before. Then after guessing the first character, which is, let's say as mentioned, this interval represents A, B, C, and then your end of the message. When you encounter B, what happens is that we can focus on this interval from 0.3 to 0.6, and then break it up based off of this new probability that we found. So in other words, 0.225 of this goes to A, 0.245 of this goes to B, and so on and so forth. Eventually what happens is that, let's say this one over here represents something like that. Then maybe the next character shall be B again, and we break that up again, A, B, and C, and so forth. Then let's say it ends at the message. Let's say this is the end of the message. Notice that this message can be represented as some number between 0 and 1. And if you as the message producer follows this protocol, and let's just say this number over here falls maybe around, I don't know, 0.451 or something like that. By following this protocol, you can send this message to someone else who's following the exact same protocol and just tell them, hey, my message ends up at 0.451. Then from there, since they're following the exact same protocol, they can reproduce the same message. And that's basically the idea behind arithmetic coding. From there, the main problem that we have right now is, initially we have some array of numbers over here, and there are two things that we'd like to do. The first is, take one of these values and then update it. When we encounter a B, we need to add 1 to this element. We need to add 1 to this element, and so on and so forth. The second thing we have to do is to be able to generate these probabilities. Actually, it's not so much that, but is to generate the cumulative probabilities. So A goes from 0 to 0.225, B goes from 0.225 to some other value, 0.675, and so on and so forth. What we need to do is to be able to calculate these values really quickly, because that's the value that we're closing in on, right? Right. So as mentioned just now, the two problems that we want to do is we need to be able to update one of these values. And also, given any of these indices, we want to find the cumulative sum from the start all the way to that index, which is known as a prefix sum. If you just store the array as is, basically like that, then you can calculate the time complexities as accordingly. Let's just say our array is of size n. Updating a single element, how long does that take? For 1, correct. It's just changing an element over an array. Yep. Then when it comes to the range sum, for example, given a range like this, naively computing the sum, how long would that take? Log n, correct? More or less the same. I don't need to explain this to you. Now from there, we can try and do some other things to maybe find some better time complexity for this. One possible idea that you can try is the extreme end. Instead of storing the array as is, you can store all of the cumulative sums. For example, like this. So given that array, what you're storing is just 10, 17, 30, 51, and so on and so forth. Just one array of entire cumulative sums, entire prefix sums. From there, if let's say you want to find the if let's say you want to find the prefix sum given an index, that's very easy. Just go down to the appropriate index and just print it out. That's all one time. On the other hand, you have the other problem. What happens if you try to update a value? I skipped something. Okay, sorry. I changed this from 7 to 27. When you add 20 to this value, how many other values do you have to change?
Everything.
Yep, everything that covers that value, which in the worst case can be every single thing down there. So your points update now takes O time. So what can you do? Well, we can possibly try and explore the same thing we did for last week, which is the idea of breaking it up into square roots and then having a summary array. Sure, that could work. So in this case, what our summary array just stores is the sum of each individual block. From there, what happens if let's say you try to update an index? So over here, if let's say that value over there, we want to update it from 35 to 54. What are the things that we have to update? The array itself, and what else?
Summary.
The summary, correct. To find that exact summary, you can just divide it by square root n, same thing as last week. So the total, there are two things that you have to update. So great, it's still O1. The nice thing is that when you do a prefix sum, for example, something like this, we can take advantage of our summary array as per usual. For every single one of these blocks which is fully covered, just look at the summary array. And then for everything that's not fully covered, we can just go through that individually. Since the summary array is of size square root n, and each one of these blocks is also of size square root n, we have our prefix sum is square root n. Great, it's better, but can we do better? Yes, we can. Right? So just a quick summary. These are the things that we have done so far. What are the strategies that we tried to employ as we went down? The idea is that we kept on trying to store more and more types of ranges. Because of that, as we go down, the idea of getting the prefix sum can be done we can get the prefix sum using square root decomposition by taking that initial range and then breaking it up into multiple parts. Because of that, we have cut down the time to square root n. If we store even more ranges, then we can get it down all the way to O1. But the problem is that there are too many things there are some elements which are covered by too many of those sums, which is why this thing blows up to On. So that's essentially what we want to do. Given a prefix range, we want to be able to partition it into some individual ranges, but at the same time in a way that no single element is covered way too many times. Fenwick, this one magical dude, decided that, hey, I know a way to partition the numbers. So let's say our goal right now is to find the prefix. I don't think I saved. Darn. Did I save? Let me check. Did I press the Control S button? That's probably why. Yeah, some things are being updated. Hold on for a while. Yeah, I did not save, that's why. Sure. Did I close it? No, I closed it. Yeah, that's why. Okay, this should be better. So yeah, let's say what we wanted to do was find the prefix sum from index 1 all the way to index 90. What Fenwick found out is that we already have a nice natural partitioning method, which is take that number, I pressed enter twice, but press and take that number and represent it in binary. This binary representation already gives us a nice simple way to partition the number. We can partition it into that kind of sum, where each one of them represents just a single bit. So 90 can be represented as 2, or it is 10, plus 1,000, plus 10,000, and so on and so forth. And each one of those values can be used to represent some portion of this large array. In which case, we can do something like that. Starting off with 1, we can use this largest bit to cover from 1 all the way to 64. Then the one after that cover from 65 all the way to 80, 81 to 88, and so on and so forth. The size of each one of these intervals just depends on that bit. So now, once we pose these questions, there are a couple of things that you want to think about. First off, how do we store these sums? How do we iterate through these numbers? We need a nice, simple way to do that. And finally, does it work? Well, first off, those numbers, and finally, we want to output the sum. What we want to do is just take all of these individual intervals, sum them all up, and then toss it back. So now we have this issue of these particular numbers. What is a nice way to get from, let's say, 90 all the way down to these values? Is there a nice pattern that we can follow? For example, from 90, how do you get to 88? What can you possibly do? Least significant bit, correct. As you'll notice, the difference between every single one of these things is that the least significant bit, which is the bit on the rightmost one, is snipped off. Take off this one, you get 88. Take off this one, you get 80, and so on and so forth. And so that gives us a nice simple way to start from your index, then go all the way down to 0. The nice thing is that at every single step, it doesn't matter what you came from. You can determine what step to go next based on your current index, which means this is nice and reusable by anything else. So because of that, this is the main idea. Given the original array A, we'll store a brand new array where every single element stores the range sum from that index all the way to that index minus the least significant bit, as seen just now. In other words, for this example just now, our array F at index 90 will store the sum from 89 to 90. Our array F at index 88 will store the sum from 81 to 88, and so on and so forth. So what does that look like? For example, this is our array over here. At index 1, if you take off the least significant bit, you get 0, 0, 0, 0. And so you want index 1 to store the range sum from 0 exclusive to 1 inclusive. For 2, if you strip off this 1, you get 0 as well. So at index 2, you want to store the sum from 0 exclusive to 2 inclusive, which looks something like that. 10 plus 37. For index 3, take off the 1, you get 2. So you want to store it from 2 exclusive to 3 inclusive, which is just at 13. Fill up the rest, you can get something that looks like this. Right? And now that we have something like this, we have a nice simple way of calculating prefix sums, which is, let's say we want to find this prefix sum over here. Our index is 7. To find it, we'll do exactly what we did before. Start from 7, take off the least significant bit, you get 0110, which is 6. Jump to 6, take that 14, take off the least significant bit, you get 0100, which is 4. Get to 71, remove the least significant bit, you get to 0, and then you stop. Because right now we'll just say that 0 is a nice stopping point. And there you go. Given this array, we have a way to calculate the prefix sums in a nice and simple way. The pseudocode is really, really simple. Now, given this kind of things, what is the time complexity? Log n. Correct, log n. That how many times you have to sum up this thing depends on the number of ones inside your original index. And given that this is an array of size n, every single one of those indexes can be represented as, every one of those indexes can be represented in log n bits. Great. Our time complexity for prefix sum is nice and simple. But the question is, how does this fare against update? We want to make sure that each one individual index is not covered by too many things. So the question is, forgot about that. The small caveat I mentioned is, the small caveat I missed is that we talked about getting this least significant bit. How do you actually do that in, let's say, a programming language? To do that, we can take advantage of how integers are stored over in most languages like C++ and Java. This is something called 2's complement. If you have taken 2100, that'll be great, you already know that. But if you don't, that's fine. Here's the question for you. If, let's say, 90 is represented in this manner in binary, what should negative 90 look like? Let's just say we're working with a 7-bit integer, because why not, right? Whatever we set for negative 90, we have to do it in such a way such that Adding it bit by bit will give us 0 as the final answer. So in this case, the last bit, which is the one right here, the rightmost bit, we know that it's 0 because we want the output to be 0. The second one, it's a 1 plus something gives you a 0, so it has to be a 1 as well. You can try that out. From there, we have a carry, you place that on top. We have 1 plus 0 plus something gives us 0, so this also has to be 1. Same thing, 1 plus something gives us 0, it has to be 0 as well. And from there, you can fill up the rest. Eventually, you have 1 plus 1 gives you 0 with a carry of 1, which gets lost because this is a 7-bit integer. All right. So in a nutshell, this is sort of what you see when you take a number and then put it and then find its negative. This is how it's represented in 2's complement, or at least in C++ and Java and most of the languages. Using this number, there's a nice simple way of extracting that least significant bit. What is it?
For only one that's not fit.
Say it again?
For only one that is not fit.
The only one that's not flipped. Okay, how do you extract that? I heard the word. It is the logical AND operator. Great. And so that's exactly what we'll do. Take the number, find its negative, compute the logical AND, and there we go. We have the least significant bit. And from there, the algorithm as done before is nice and simple. It's nice and complete. So yeah, the next thing to mention was that other thing just now. How many of these intervals are actually covered? Sorry, given an index, how many of these things do you have to update? Oh, sorry, there you go. That's exactly how you do it. As mentioned just now, let's say you update value now. Let's say you update index number 5 from 9 to 29. Given that our Fenwick tree currently looks like this, the values that we have to update are everything that covers index 5, which would be this thing, and that thing, which is like that. So in this particular case, there are 3 things to update. What about in the general case? Can we find out a way to can we come up with a way to find out how many intervals have to be updated? And more importantly, can we iterate through them? Is it more important? I'm not sure. But yeah. Well, from starters, what kind of indexes do you have to consider? Based on the definition of our array F, it's any single index I such that if you strip off the least significant bit, then this thing is caught in the mess. In other words, what? Oh, sorry about that. Yep, those things are the ones you have to update. Basically, we have to update you have to update Fi for any index I which falls inside this range. The value itself has to be at least as large as the index you're updating, and when you strip off the least significant bit, it has to be smaller. From there, you can try and play around with a few things. You can find out, for example, 164 is not an index that you want to update because, oh, I got it wrong. Okay, basically when you subtract out the least significant bit, it is still too large. It is not lower than 90. So 164 is not a thing that you update. Same thing, something like this, for example, 69 and 68. This value is too small. It is not small. It is not as large as 90. So that's not the thing we update. Another thing we'll try. Okay, 92 does work. 92 is at least as large as 90. And when you strip off the least significant bit, we have 88. That's smaller than 90. Great. So what kind of patterns do these indices follow? Well, Fenwick didn't actually mention any of these things in his paper, so I tried to come up with some patterns myself. First off, given this index, we are stripping off the least significant bits, correct? What does this look like? What does everything after the least significant bit look like? One proposition I'll claim is that whatever is left over after you take off the least significant bit must match the index that you're trying to update. In other words, something like this, for example. After I strip off this least significant bit, everything else after it must match the index. And you can see for yourself why that should be the case. If it doesn't match, that means this portion is either strictly larger than this portion, or is strictly smaller than that portion, and that causes problems. For example, something like this: if this portion is already larger than whatever we're dealing with, which if you take out the least significant bit, it's still going to remain larger than the index that we're trying to update. Same thing if it's already smaller, it's going to remain smaller after you take out the least significant bit. So there, we have one proposition. This is one necessary condition. So next thing, where should that least significant bit be? Well, I claim that it can't possibly be too small because that's also going to be a problem. For example, something like this. the least significant bits of I cannot be smaller than the least significant bits of the index you're trying to update. In this example, it does work. See, the least significant index is larger, it's not smaller. If it happens to be smaller than the index, then what happens is that based off of our previous proposition, everything after this index must match. Everything after the least significant bits must match the index that we're trying to update. And from there, you'll realize that you'll realize that after taking off that bit, what you're left with is a number that is exactly the same as the index that we're trying to update. So that's not going to work. All right, so now we know the least significant bits cannot be too far to the right. Can it be anywhere in this middle? The answer I claim again is no. Here's another proposition. The least significant bits of the thing that we're trying to update, of the index I, cannot be one of the 1 bits inside the index. What does that mean? Here's an example. This is an example that works. The least significant bit is not one of the ones inside the index that we're trying to update. Okay? So what happens if it does match? Well, what happens is that after you take it off, that's great, it is smaller, but because it is not the least significant bit of the index that we're trying to update, we realize that because everything else is the same afterwards, this number that we started off with is strictly smaller than the index that we're trying to update, right? And now we have three necessary conditions of what this index I will look like. And with a little bit of extra work, you can find out that these 3 conditions together form a sufficient condition, which is any index I that follows those 3 propositions will be an index that we're trying to update. And as mentioned just now, if it matches, if the least significant bit matches, that means we have I being equal to the index itself, and yes, that's definitely something that we have to update. So from there, we can generate the list of indices that has to be updated based off of the initial index. You can take a look through them. We start out with the original value up there. Then from there, we know that the least significant bit must match one of the zeros up in this index up here. So as you go along, you can see what it looks like. And I'm just going to claim that these are indeed the indices that you're going to find. As mentioned just now, that's how I update it. So now the question is, how do you easily iterate through them? Starting from 90, how do you get to this, to this, to this, to this? Is there a nice, simple way? Does anyone have an answer?
Don't you just plus 1 to the least significant bit?
Correct. From 90, what you want to do is just add the least significant bit. From just now, we subtracted the least significant bit. Here, we're going to add it. By adding to the least significant bit, we are jumping from here to the next 0, and then so on and so forth. And these are the values that you have to update. And great, we have our update. We have our update operation. It's nice, short, and simple. Great. In terms of time complexity, what is the time complexity of this operation over here? Log n as well. What kind of justification can you say? How do you reason about it? Yeah, sure, that works. Sorry. So essentially, within our table, we have a table of size n, and so we have log n. So we have log n bits to play with. The least significant bit, as mentioned just now, can only be the same as the original index, or any one of the zeros of that original index itself. So you can also claim that it is indeed log n as well. There's a small disclaimer at the bottom. You don't have to care too much about that. It's quite common sense. And from there, you'll notice that within our query and our update, we have formed 2 implicit trees per se. When you're trying to query an element, you start from a value and then subtract off the least significant bit. This is what the tree sort of looks like. And on the other hand, if you try to update something, you go in the opposite direction. Keep going up until you exceed the size of the tree. The next operation I'll talk about will be what happens when you want to initialize the tree. You're given the array A, and you just have your tree, and you just have your empty tree right there. How do you take these values and then populate them inside? The simplest way, of course, is just to call update multiple times. Sure, that's great. That's gonna work. It's nice and simple. It's like constructing a heap from an array. You just push it in one by one. It works. And it does indeed give you a time of n log n. Can we do better?
Yes.
What can we do? So in this case, what happens is that we'll take this 10 and then update. Plus 10, plus 10, plus 10, plus 10. Then go to 27, plus 27, plus 27, plus 27. 13, plus 13, plus 13, plus 13. Notice that we're going through the same vertices multiple times. Can we cut down on that? How do you do that? What would the pseudocode look like? Any takers? All right, the crowd is roaring. As mentioned just now what I mentioned just now was a sort of hint. The idea that you add 10 multiple times throughout the same chain is a bit of a repetitive step. Why do we need to do that? So instead of having this 10 propagate all the way up, we have that plus 10, it's going to go up. We have that plus 27, it's going to go up. Why not put them together? That is, take this plus 10, move it up here, but hold on for a while. We'll take this 27, place it there, and then we'll push both of them up together. In which case, that'll make things simple. In other words, we're iterating from the tree, from the bottom all the way to the top. And because this update tree is nicely arranged from left to right, our solution is as short as this. Yay! Nicely done. Essentially, take every value inside A, initially copy it inside. So right now, 10 is here, 27 is here, 13 is here, and so on and so forth. Eventually, this 10 is going to be pushed all the way up. This 10 is going to be pushed when you're processing 1. The 10 will be pushed up when you process 2. The 10 will be pushed up when you process 4, and so on and so forth. And there you go. We're touching each vertex exactly once. And now we have it down to n. And there you go. Finally, this is not something that Fenwick needed, but we have a last operation, which is arbitrary range sum. So instead of the sum from the prefix, from the start all the way to some arbitrary vertex, let's just say I have a start point, I have an end point. How do I find this range sum? What can I do? Subtract, correct. We have the prefix sum at the end. We have the prefix sum, everything else from here. And so we can just subtract it. Nice and simple. Time complexity is just the time complexity of prefix sum, which is log n as well. There you go. You now know the basic operations of a Fenwick tree, and as I described, they are so simple that you can just code it off the top of your head immediately. It's nice and simple. It's nice and simple.
106 flex.
Yep. Because of the simplicity of the code and how easy it is to use it, it is very commonly used among competitive programmers or anyone who wants to try and solve one of those Cantus problems. If you need a data structure that needs to support range sum and points update, the Fenwick tree is usually the thing to go to because it's so simple to copy and paste. And if you don't have something to copy and paste, you can just code it on the spot. It's going to take you less than 2 minutes, as you can see. Great. And you don't necessarily have to use a Fenwick tree with just addition. The Fenwick tree works with any kind of operator as long as it satisfies a few things. For the points update and prefix sum, the only things that we need to make sure of is that it satisfies the associativity operation, such that we have to make sure that the operation is associative. Because what we're doing is we're getting the sum of this portion and then this portion and then this portion individually, then combining them together. As long as they're associative, we can do that. If it's not associative, then tough luck, you can't use it. Finally, if you want the range sum, all we need to do is that in addition to the associativity, we need to be able to subtract off that thing at the start. For addition, it does work because we can just minus it off. But for an operation, for example, like minimum, if you want to find the range minimum of some arbitrary range, we can't take the minimum of this range and then subtract off this range. That's not how minimum works. So unfortunately, that's not how it works. We need to make sure that it is invertible, so to speak. Some examples of that, in addition to addition, is multiplication or the XOR operation. Those are things that work. And there you go. One small disclaimer is that this way of performing the arbitrary range sum cannot be done if it's not invertible, but it doesn't mean that it's impossible to use a Fenwick tree to find an arbitrary range sum. If you know how to do it, I suggest you keep quiet, because it will help you out for this coming weekend. Let's just say that. All right. As mentioned just now, the Fenwick tree is best used when you find out that you need those two operations, point update and range query. More often than not, you'll find a problem that doesn't tell you outright, hey, I want you to come up with a data structure that can point update and range query. No, you don't get it. You don't get that nice silver platter. No, you get the silver platter buried under a gigantic pile of rubbish. Yeah, that sounds nice. You need to clear out all that rubbish to find that silver platter on the bottom. In other words, more often than not, you have to take your problem and maybe transform it in such a way such that it's now solvable using point update range query. All right. Are there any questions with regards to Fenwick trees for now? Yes.
So just now you had the AND operator with the two's because it's a two's complement. But what happens if your program? I don't know if there are languages that do use two's complement, but in such scenario, what should we do to find the least significant?
Good question. In cases where you have binary operate, in cases where you have programming languages which don't use two's complement, but still store positive numbers in binary, we can still make it happen using some other method, which I hope this has Notepad++. It doesn't happen.
If it's one's complement, then it's plus one.
Is this big enough? Hope so. So let's say this is the number where you want to extract this little one here. Assume that you still have those bit operations such as AND, logical OR, and XOR, and so forth. What we can possibly do is get rid of this one, and then maybe put all the, actually no, not too sure how to explain it, but this is one way that you can possibly do it. Basically, you want to generate some number where that least significant one is no longer there. What can we possibly do? You can, I think I heard it somewhere, you can subtract one.
And then end it.
What do you get? You get that.
Yeah,
And once you have that, you can perform your standard logical AND, and there you go. You have extracted off the least significant bit. So this helps you out for your points. This helps you out for your range, for your prefix sum. If you need to actually get the least, you can actually. If you actually need to extract this one bit by itself, all you have to do is just take this and then minus it off. Correct, I heard that just now. And there we go. It is indeed possible. I'm not too sure what languages actually do this. I don't know, maybe big integer in Java, I'm not sure. Oh well. But yes, that was actually something that Fenwick mentioned inside his paper as well. Pretty interesting. Excuse me. Right, are there any other questions? If not, let's get into a small little problem that uses the Fenwick tree. This problem is something I like to call the farmer's indecision. This is not a well-known problem, it's just something I cooked up off the top of my head. So here's the idea. There is currently a farmer who is really indecisive, as the problem suggested. What he wants to do is water his crops, but he doesn't know how much water each individual plant should get. Maybe he wants, let's say, 5 liters of water for this plant, 10 liters of water for that plant. You're not sure. The point is, you are stuck with him. You are the one working under him, and sucks to be you. You are the outlet for his rants and tantrums. So he will constantly shout at you, asking you to change the amount of water that you water the plants with. So initially, let's say you have your plants arranged nicely from one all the way to n. The farmer will now shout at you 2 different types of queries. There is Telegram. I should probably delete that. I should probably close that. Elder, that was you.
No, you had notifications on.
No. Right. The first query that he says is that. First query. Damn it, worker, this isn't working. Pour X more milliliters of water between plant A and plant B, inclusive. So an example of one of these queries could be maybe X is equals to 25, A is equals to 5, and A equals to 8. Essentially, that means he wants you to pour 25 more milliliters of water between these 2 plants inclusive. So in this case, they should have 25 more milliliters of water. Okay. And maybe another one could look something like this. The value of x can also be negative, which means he wants to decrease it. Okay, so minus 3. These plants which have 25 will have 22 milliliters of water. And those 3 plants at the end, well, they're going to die. All right? They're going to die. Yes. Negative water. I love it. Okay. That's the first kind of query. The second type of query is that he says, this world is going to burn before I get this thing done. Worker, how much water is plant C swimming in? C in this case is just some index within the list of plants. So for example, if the query came in with C is equal to 7, then you just want to output 22. Sounds simple enough. But right now he'll give these queries to you back and forth, back and forth. What you have to do is to be able to support each one of those queries as fast as possible. You may have to perform some pre-computation, that's perfectly fine. But the point is that you want each query to be as fast as possible. So what can you do? If let's say you just have a standard array, just store that array by itself, well, you already know how slow that's going to happen. If you want to change the value of the water within a range, that's going to take for one time, depending on the size of the range. But guessing the amount of water is for one time. Nice and simple. Question is, can we do better? Here's the answer, we can do better. So what can we do? Well, you are lazy. And that's perfectly fine. You can be sorry about that. Ellen is dying now. Okay? You are a lazy worker. You want to be as lazy as possible while still getting the job done. So what do? Well, right now the farmer is just shouting his head off, and you don't actually have to water the plants just yet. You're just sitting there waiting for the time where he sends you off. So right now you decide, how should you water the plants? You look in the corner of your eye and say, oh, the tractor is right there. Let's use it. So you can make use of the tractor. Good for you. I love the fact that some people are laughing, they recognize what it is. All right. So the answer is, why don't we use it? So here's your grand plan. What you're going to do is you're going to set up the tractor right at plant number 1 down there. And instead of watering each plant individually, what you're going to do is just hold the hose while you turn on the tractor and keep on going. Essentially, as you go down the plants, you'll just adjust the hose as accordingly. So as it goes down, for example, as it goes here, okay, you're going to turn it up to 25, turn it down to 22, and then turn it down to -3. So that's your grand plan. Sounds like a plan, sounds like a great plan. So what do you need to do to execute this? Well, all you really need to do is to know when to you need to know when to adjust your hose and by how much. So let's just say we'll just store that inside some data structures, something like an array. So it's going to look something like that, which means when you reach index 5, you should turn it up by 25. When you reach index 7, you should turn it down by 3. When you reach index 9, you should turn it down to 25 so that the hose is spitting out things from the underworld. And finally, at index 12, you should put it up to 3 so that you're stopping. All right? Now let's model this problem around this adjustments array. How should this thing be modified so that you can answer both those queries? First query: what happens when you want to update a block of water? If let's say you want to add 15 to this block of water, what should your adjustments array look like? What should it do? A few murmurs over here. Anyone have a concrete answer? What should you do? All right, I saw a few hand gestures. I think you guys got the idea. Based on how we define this adjustments array, if we add 15 to this range, that means when we get to plant number 3, we should turn up the hose by 15, and after we pass by plant number 6, we should turn it down by 15. So that's exactly what we're going to do. So that's what we're going to do right there. The second query, which is how much water is a plant getting? So in this case, number 22. How can we answer that using the adjustment array? Well, to find out how much water you're trying to put out, I heard it just now over there. You can simulate it in your head, which is you start from the front and you adjust your hose accordingly, which is you take all of the adjustments up to that plant and sum it all up. All right. So there you go. Now you have modeled the problem in terms of this adjustment array, depending on what your data structure needs to support is that you need to be able to update individual points, and you have to find the sum from the start all the way to some arbitrary index. That is exactly what the Fenwick tree can do. So take your adjustments array and then model it as a Fenwick tree. There you go. Now you have your points update, now you have your prefix sum. Everything can work in log n time. Great. Your life is now logarithmically easier. And at this point, technically I have another problem that I want to go through, but I didn't have time to put inside my slides.
Is it range?
It's not range update, range query. We'll cover that later. Sorry, next week. So here's the second problem that I'd like to model for you. This is a problem on Catis because I am unoriginal and I get my problems from Catis. But here's the idea. You have a list, you have a stack of movies where these movies are contained in their own DVD cases. Okay? Right now we have, let's say, these ones over here. Something like that, let's say. Right now they're all nicely arranged 1, 2, 3, 4, 5. Okay? We have a total of n movies in this case. And what you're going to do is that you are going to watch these movies as much as you want. But how you're going to do that is, first, you will select one of these movies to watch. Let's say we decide to watch movie number 3. What you're going to do is remove this movie from the stack. Everything else is going to drop down onto it. This is 4, this is 5. Something like that. Then after you're done watching that movie, you're going to put it back on top. Sounds simple enough. The number of times that you're going to watch these movies is a total of q. So it means if q is equal to 5, you'll be watching 5 of these movies, not necessarily uniquely. You may watch a movie more than once because you're forgetful like that, or you're just really nostalgic. What I want you to do every time you watch a movie, I want you to output how many movies are on top of that thing when you pull it out. In other words, if I say I want to watch movie number 2, what I want you to output is the number of movies on top of it, which is 3 movies. You pull this thing out, everything else will drop onto it. Then once you're done, you place this movie back up there. And then you'll keep on doing these for a total of q iterations. For simplicity, let's just say that q is somewhere around n. Yep, it is indeed. So let's just say q is on the order of q is somewhere around the order of n. So that is the problem that I pose for you. It may be possible to solve this using something like an ordered statistics tree if you're familiar with that. But in this case, how can you possibly solve this with the things that I've taught you so far? Again, q is a reasonable number. For example, q plus n, it's okay to store that inside your array. Right? So that's the problem that I'm going to give you. 5 minutes. You can discuss. Or maybe around 3 minutes. Sure.
So he's asking after and watching the movie and then what's his stack like?
No. Every time you remove a movie, you answer how many movies are on top.
That's the CEO.
Oh, okay. What do you return for the using
The number of CDs on top.
Just
on top of yes.
Yeah. I mean, if you use PVDS, it's just rank.
Oh.
So basically, it's asking you to use memory tree to solve that.
Space tree.
We call it 360 seconds.
Stop it.
Actually, be lazy with the family tree.
Don't shake the table. Check against the side.
I haven't been timing, but who cares? This is the problem. Does anyone have any ideas that they like to voice out? For those people who have seen this problem before, try to hold back. Right. Anyone? Do you guys have any ideas?
N plus Q size.
Sure, that works. What do you do with that?
So every time you query, you move it to the Q side.
Move it to the what side?
The N side, so that's why you initialize it.
Okay.
Then every time you query, you just move it into the Q side, right? Yeah.
So in this case, let's say I pull out movie number 2. What am I going to do?
I will minus 1 on the N side at the second one.
You minus 1 on the side? What do you mean by that?
I minimize all N to 1.
All ends to 1. Okay. So what's going to happen?
Move the H by move, so I get minus 1.
Okay.
And I will have 1 on the Q side at all.
Okay. So how do you answer the query?
I just do Fenwick tree, sum everything on top.
Yeah, there you go. And that is a possible way to solve this problem using a Fenwick tree. Remove the idea of everything falling down when you pull out a movie. When you pull out this movie number 2, I'm just gonna say, screw the rules of physics, those things are gonna float. So now movies 3, 4, and 5 are still inside indices 1, 2, 3. So movies 3, 4, and 5 are still within indices 3, 4, and 5. That's fine. When I put back movie number 2, I'll place it on top, which in this case shall be index number 6, a brand new index that I've just created. And to find out how many movies are on top, it's exactly as you mentioned just now. We'll just have a Fenwick tree to represent how many movies there are in each slot, using just a bunch of zeros and ones. Sorry, 0. So initially what we do is we initialize a Fenwick tree of size n plus q. Because eventually that's how large our non-physical stack is going to be, right? So when you remove movie number 2, all you need to do is just remember which index that movie is currently stored in. And we can do that using a separate array. So this is the position array. Initially it's 5, 4, 1. Take out movie number 2. Where is it? It is at index 2. All right. I'll take this out. To find out how many things are on top, I'll just do a range sum from index number 3 all the way to the top of my stack, which is n plus q. Then I'm done. What I'm going to do now, I'll remove it from the stack. From there, in my Fenwick tree, I'll say that this thing is now vacant. At index number 2, remove a 1. The top of the stack right now is index 6, so I'll place movie number 2 over there. In my Fenwick tree, I'll say that there is something in index number 6 right now, plus 1 for that value. And then finally update this thing over here. Movie number 2 is now in slot number 6. And then you can keep on doing that as much as you need to. The amount of operations that you'll do for each one of these queries is we'll have to set this to we'll have to minus 1 at this index, plus 1 at the new index. So we have two iterations of points update. And to find everything on top, that's one iteration of range query. So there you go. Within this n plus q size Fenwick tree, each operation takes a lot of n plus q. And that is great. In the context of this Cassis problem, both n and q are around the values of 100,000. So this works. Great. And that is in general the problem. If you are in dire need for Cassis points and you don't have this problem solved yet, there you go. You have one new problem to solve.
But that means you also have to store the current maximum index.
Yeah.
Correct. You do have to store your current maximum where the top of the stack is right now, which will just be one extra bit.
I in range Q.
A small
Yeah.
A small challenge for you is that right now the size of our Fenwick tree, as well as the overall time complexity, does depend on Q. My challenge to you right now is, probably not right now. My challenge to you is find a way to do it such that Q is no longer in that time complexity, which means I can do each query in log n time. Here's a hint: amortized log n time. If you have the answer, keep it to yourself. It will come in useful.
What is Leslie just now?
Or if you want to share it, sure, that's fine. I'm already fine. I don't really care about weight either. So those are the two problems. So those are the two problems that I have prepared for you. Before we go for a short break, I guess I'll give you the third problem that I remembered. I won't go through the solution right now, but we can
So basically, the laws of physics don't work.
Not wrong. What if it's a zero? That means there's nothing there, right?
Right. Here's the last problem that I'm going to go through with you. I will initially give you an array of numbers ranging from 1 to n. All of these numbers are unique. Each number appears exactly once. I'm going to do this set of operations right now. In my first step, I will find the number 1 and then move it all the way to the end, move it all the way to the left end by the use of swaps in the same way I thought this would. So in this case, what I'll do is I'll find 6 over here. So in this case, I'll swap 2 and 1. Then I'll swap 1 and 6. A total of 2 swaps was performed when I did that first operation. In my next step, I will find 6, the largest value, and then move it all the way to the right end. So 6 will swap with 2, and then swap with 4, swap with 3, swap with 5. Eventually you get it over there. There are a total of 4 swaps, so I'll just keep track of that. The next thing I'll do is I'll find value number 2. Then same thing, move it all the way to the left. Then I'll find value number 5, move it all the way to the right, and so on and so forth. So it's 1, n, 2, n minus 1, 3, n minus 2, and so on and so forth. And every single step, I wanted to print out how many swaps did I make, right? So that's the problem, if you're interested in. The problem idea is called turbo. I will not be going through this, but you can think about it. I can provide a solution if you want. But in that case, let's go for a short 8 to 10 minute break. 8.